I am going to demonstrate how we're going to work with differentiating with respect to x and also differentiating implicit functions. It, in the long run, is fairly simple, but until we're used to it, it is going to be pretty strange. So let me show you how this is going to work. So let's start with an example. So let's say I want to take the derivative of x cubed, not x squared, x cubed. So my variable that I'm differentiating with respect to is the same as the variable in the function. So I'm just going to apply the power rule. And so I get 3x squared. So that is when the variables agree. So variables agree. Now, what happens if the variables don't agree? Let's think about what happens if I take the derivative of y with respect to x. Well, this variable and this variable don't agree. But y is a function of x. So, as unexciting as this is, I get dy dx. Nothing new, we've worked with this before. Now, what happens if we have something a little more complicated? So what about the derivative with respect to x of y cubed? Well, I'm going to note that the variables don't agree, but I'm assuming that y is a function of x. So I'm actually going to use the chain rule. And the chain rule says that I'm going to take the derivative of this. So I'm going to choose a u. I'm going to say let u equal y of x. Now I'm putting the of x explicitly. So that means I'm going to take a derivative with respect to u. And that derivative is going to be 3 u squared u prime, but my u prime is just the derivative of y, so I can rewrite this as 3y squared dy dx. So for convenience sake, I am going to skip this part from now on. I'm going to automatically assume that I do the substitution for the chain rule. So let's try something just ever so slightly more complicated. So now I'm going to mix it up. I have a function that is both in terms of the independent variable, the x, and the dependent variable, the y, and I'm still differentiating with respect to x. So I'm actually going to do this. I can distribute the differentiation across the addition sign. So I get d dx of x plus d dx of 3y. And now derivative of x with respect to x is 1. Derivative of 3y with respect to x ends up being 3 dy dx. Okay, so that wasn't too bad. Now, what if we have something ever so slightly more complicated? Now, before we had the sum of two functions. Now let's have the product of two functions. So I have x times y squared. Now I differentiate, and I end up getting, by using the chain rule, by using the product rule, I'm going to have x d dx of y squared plus d dx of x times y squared. Okay, now we're going to simplify. So equals, I'm going to bring my x down, d dx of y squared, I'm going to use the chain rule, and more specifically the generalized power rule. So I get 2 y prime. So I'm using prime notation just for ease, and the prime is the same as dy dx. Then I add it to d dx of x. So the derivative of x is 1 times y squared. And now I have x times 2. Well, here, let me put it in a more conventional notation. We should put the coefficients up front. So 2x, y, and I'm just rewriting that y prime as dy dx plus y squared. And that is differentiating that is implicit differentiation.